All right, now up to this point, everything that we've been working with has been an explicit function. An explicit function is something that looks like this. It's an equation where it's already been solved for a single variable. So in this case, it's y equals, and there's no y's on the other side. That would be considered an explicit function. It's what we're used to. Today, however, you may end up feeling a little bit uncomfortable with some of the stuff we do because it's actually with implicit functions, implicit equations. But that uncomfortableness is mostly just because we're going to be having equations that don't look like what we're used to. It's not that it's out of the realm of ability or anything, it's just getting used to it's okay if it looks like this. So know that you might not feel like it's all going smoothly right away, but that you'll get there because you get used to it. So this is an implicit function because you'll notice it's not just y equals or x equals or z equals or anything like that. We have on both sides a mix of things. And so today is all about finding derivatives of implicit functions. This is the first problem we're going to be doing. Write this down, and of course all the other problems that we end up doing from here forward. Now for this first equation that we work with, this is an implicit function, but this particular one could be derived using a couple different methods. The first is a method that we already know. We can actually start by just writing this as an explicit function and then taking the derivative using all the rules we already know and love so well. So for this first time through finding this derivative, I want to write it as an explicit function. In order to do so then, what do I do to both sides of the equation first? Yep, divide by 2. So start by dividing both sides of the equation by 2. And remember that as you do so, you're dividing everything on both sides of the equation by 2. So we've now written it as an explicit function, which means now we can figure out what the derivative is. We can figure out what y prime is using all the rules we already know and love. So go ahead and find the derivative then of the right side. You're using power rule here. And you should find that y prime equals 8x cubed plus 16x. Now, it might seem obvious here, but I just want to remind you about why we write y prime. Remember that y prime means derivative of y. So that's why the y becomes y prime, because I'm taking the derivative of everything in this equation. And when I take the derivative of y, that gives us the derivative of y, or in other words, y prime. Seems simple, but that idea is something that we sometimes gloss over, and it causes us problems here in a moment if we don't keep that in mind. Right, now we're going to solve that equation implicitly and see how implicit differentiation works with this sort of thing. Now, implicit differentiation means we don't try to solve it to be y equals or anything like that. Partly because when we try to solve them for y, sometimes that gives us really messy looking equations later. And partly because when we try to solve it for y, some of them are basically impossible to solve for y. And so we have to have implicit differentiation as the tool to be able to deal with those. All right, so to derive this implicitly, basically we are just taking the derivative of both sides of the equation as we see it. So that means first finding the derivative of 2y. Well, remember it's a constant times something. When we find the derivative of the constant times anything, it always is, the result is always 2 times that derivative. So I know it's going to be 2 times the derivative of y. And what is the derivative of y? Y prime. That's why I was making that emphasis on that last problem, remembering that y prime just represents derivative of y. So when I have to figure out what the derivative of y is, I just plug in the y prime, wherever that happens. Now we did the derivative of the left side. Let's go ahead and do the derivative of the right side. Now on the right side, though, we're taking the derivative with regards to x. It's always assumed to be the derivative with regards to x unless you're told otherwise. So the right side derivatives are going to work like they always would have. So I'm just going to use power rule on the right side. So 4x to the fourth becomes 16x cubed plus 32x. And then the derivative of 2 is 0, so that drops out. So this is the first step of finding the derivative implicitly. And really, technically speaking, we've done the derivative. It's just not how we want to leave our final answer, because I'm trying to figure out what the derivative equals. That means I really want an answer that is written in terms of y prime equals. Okay, so that means I got to do a little solving here at the end. So again, to get y prime by itself, in this case I divide by 2 again. So divide everything on both sides by the 2 to actually figure out what y prime equals. When we do that then, that gives us 8x cubed plus 16x. The same thing we got using the explicit method that we did in the last problem. Thank goodness they both work and give us the same answer, or we'd have a big problem. And so, though this does give us a way to see how the implicit differentiation can work. Now, of course, it can feel uncomfortable still. It looks weird, and it feels a little weird at first. So we're going to be doing more practice with this to start seeing how it really gets used, and just to kind of get more used to seeing it and feeling it. So to continue getting used to and comfortable with these types of problems, we're going to find this derivative implicitly. And again, implicitly means you don't need to try to solve this to be y equals first. Instead, I'm just going to take the derivative of the whole left side and the whole right side as they stand. Which means the first derivative I need to take is the 3y. Again though, it's just a constant times y. So I know my derivative will be 3 times the derivative of y. And the derivative of y, of course, is y prime. Remember, it has to be y prime because we're taking the derivative with regards to x, not y. All right. So plus, now the derivative of 7x is 7 times the derivative of x. Since we're taking the derivative with regards to x, the derivative of x is just 1, which is why that's 7. So notice the difference between the derivative with regards to x or y. The y has to stay the y prime. The x, we use our normal rules like we always have. Which means the derivative of x squared is a lot easier. Derivative of x squared is 2x. Now, having done that, again, we want to know what y prime equals, so go ahead and solve this to be y prime equals. And so when you solve this to be y prime equals, you subtract the 7 from both sides, 2x minus 7, and then you divide both sides by 3. So we get y prime equals 2x minus 7 over 3. So again, this allows us to know what's the slope of this function at some x value. And I can actually plug that in and figure out what the y is. Now, you've done a couple of these. I want to see if you have this basic process down, so write down this problem and then go ahead and work it through. You might hit a wall at a certain point in terms of actually working it through. If so, at least work up until you find out where that wall is so that we can work from there. All right, and again for this one, if we're going to find this derivative implicitly, we're just going to find the derivative of everything on the left and right sides. So we start with the derivative of the 3x to the 5th. Oops. That gives me 15x to the 4th. It's only got x in it, so it just follows all the same old rules that we already know. Plus, now the derivative of 7y would be 7y prime. Now, on the right side, derivative of x is 1 minus, and then the derivative of y, again, is y prime. And we want to solve this to be just y prime equals, because I want to actually be able to just use this to plug in some x value and find out what the slope is, the rate of change is, the derivative, in other words. So I'm going to go ahead and add the y prime to both sides. And then I'm going to subtract that 15x to the 4th. and then divide by 8. So we get y prime equals 1 minus 15x to the fourth over 8. And again, that's a function now that tells us exactly what is the derivative at any given x value. All right, now for this problem, this one's different from the previous ones because it's no longer just a constant times y, it's y squared. And you're going to see that adds some complexity to this process. It also starts revealing why we need to have this special implicit differentiation process. So, let's see how to deal with this. This is where things start getting tricky. Again, if you feel uncomfortable at this point, that's a little bit okay because this is going to look different from what you've seen before. But it's only uncomfortable because it's not what we're used to seeing. Not because it's so difficult or way out there, but because it's different. And so it's a matter of getting used to seeing that this is going to be okay. All right, I need to find the derivative of y squared. Now remember that theoretically, I could figure out what y equals. Y equals some function that involves x. So really what we're doing here is we're finding the derivative of some function involving x squared. Well, if I'm trying to find the derivative of a function squared, which rule do I need to use? Chain rule, because it's something involving x squared. And so if I use the chain rule with that kind of thing, I'm just leaving that little box with x in it in there in the moment to help visualize, that would mean that I have to do 2 times that box times the derivative of that box. Now, I don't know how to write a box prime or whatever like that. So instead of writing it with that box, that's why we then say, okay, well, it's y, right? So then it's really 2y, so that's the derivative of the outer, times the derivative of the inner. The derivative of y is y prime. That's really what we're doing here. This stuff was just kind of help us visualize why we have to use chain rule. No, you aren't actually writing that. And so the derivative of y squared is 2y times y prime because we have to use chain rule. So again, the 2y, that's derivative of the outer. Y prime is derivative of the inner. And that equals, now we do the derivative of the right side. Thankfully, that's easy. It's just x's, right? So that becomes 3x squared plus 7. All right, and now like the previous problems, we need to get this in terms of y prime. We need to know what does the derivative actually equal. So if I want that left side to just be y prime equals, what do I do to both sides? We divide by the 2y. And so let's divide both sides by 2y here. And when I do that, yes, on the left side I get y prime equals, which was my goal. On the right side, it's 3x squared plus 7 all over 2y. And remember how I was saying that this is where things start feeling uncomfortable? This is why. Because all of a sudden our derivatives no longer just equal something in terms of x. Our derivative now equals something in terms of both x and y. So like if I was trying to find the slope at a certain point, I'm no longer just plugging in the x coordinate. I'm now having to plug in both the x and y coordinates of that point to find the derivative at a specific point. Now, having found that, I do want to bring up one other thing here. Could we technically have solved our original equation to be y equals at the start? Technically, yes. If we had done that, you would have had y equals plus or minus square root of x cubed plus 7x minus 1. Now think about what would be involved in finding the derivative of this. That'd be kind of messy and ugly, right? In fact, it ends up being much easier, really, to just find the derivative using the implicit differentiation this way. That's partly why we have this method. So it's partly because it makes these easier to solve. And it's partly because some of them are actually impossible to solve to be y equals. All right, we're going to do one last example together here. Go ahead and write down this problem. And as you're writing it down, do you recognize this equation? If I graphed it, what would it look like? It'd be a circle. Yeah, this is the equation of a circle. And so, all of a sudden now, I don't have to solve it to be y equals some plus or minus square root or something like that. I can find the derivative implicitly, whereas I wouldn't have been able to do it very easily before. So, go ahead and first try to find this whole derivative implicitly using the last problem that we did as an example. Again, see how far you can get. If you can't get through it all, that's okay, but at least get through as much as you can. Then we'll go through it together. All right, so to find this derivative, again, we're doing it implicitly, so we're going to do the derivative of everything on the left and the right. Derivative of x squared, that's the easy part. That gives us 2x. Plus, now the derivative of y squared. Again, we're using chain rule like we did in that last problem. So it's first derivative of the outside, which is something squared. So that gives us 2 times the something. And then that is times the derivative of the inside. The inside is y. Derivative of y is y prime. Equals. Now the derivative of 25. What is the derivative of 25? 0. Yep. So the whole thing equals 0. Now we're down to algebra work. I got to solve this to be y prime equals, because I want to be able to have some little function that tells me what's the slope at any given point. So first thing we're going to do there is I'm going to subtract that 2x from both sides. That gives me 2y y prime equals a negative 2x. Now I want to divide both sides by 2y. So that gives me y prime equals. Now before I reduce, that's negative 2x over 2y, but yes, I do want to reduce that. And so if I reduce that, a negative over a positive is a negative, and then the 2's cancel, leaving me with x over y. So y prime here equals a negative x over y. And that's our final answer. Notice what this does then. If I have some point on the circle, I can plug it in now and figure out what's the slope. For instance, knowing that this is a circle here, let's say that x was 0. If x is 0, what's y? If x is 0, y could be either 5 or negative 5. I'd want to know which one I'm working with in order to find the slope at that point. Hence why you'll notice that our equation has both x and y in it. Because there's multiple y's that could go with that one x. And so, for instance, I might pick that it was actually going to be the 5. And so I could say, okay, well, at the point 0, 5, I can plug that in and figure out what my slope is. And so that's partly why you can see then we end up with equations that have both x and y in them. It's, again, not what we're used to, but it is something that we can then make use of in ways that we couldn't have necessarily made use of other equations before.